All right. Well, welcome back, folks. Let's go ahead and let's get started. I'm sorry. Before we get started, I think I had mentioned then that on Monday, I'd like us to meet live during our class period, so we can talk about how we're going to finish up this semester. Okay. So please, on Monday during our class meeting time at 12:50, please log in to Zoom. I'll post the Zoom material again for us. That way, then you'll have that information there so we can meet on Monday. Okay, so um, at that point, then I'll update you on how we'll finish up the semester and what we'll have to do. Okay. All right. So let's go ahead and let's pick up where we left off with yesterday, and we were talking about this third case of the free fall. And remember, free falling objects. There are a couple of criteria that we use to describe an object that is in what we call a free fall. A free-falling object, is an object that's moving towards the center of the earth. That is, it's falling down, in this case then, towards the center of the earth. That's the first criteria for a free-falling object. Secondly, then, for a free-falling object, then we're going to ignore the air friction, which is drag force. We're going to make sure we ignore that as well. So any object that's falling towards the surface of the earth, that is, any object that's moving towards the center of the earth without any air friction, that's an object that is in free fall. Okay. The reason for that, then, the reason why we describe that, then, is if that is the case, then the acceleration on the object, that is, an object that is in a free fall, the acceleration will always be constant. It'll always be the same, and the value then would be 9.8 meters per second squared. Okay. So that is the acceleration, and that actually is the one criteria for an object in free fall. Okay. The one criteria for any object in free fall is that it is accelerating towards the center of the earth at a rate of 9.8 meters per second squared. So it's a constant acceleration for any object in free fall. Constant acceleration, and this is constant non-zero acceleration. Okay. So if that's the case, and if that's the only criteria that we use to define then a free falling object, then there are three different types of free falls that we've talked about. Okay. So the very first type of free fall then is an object that is dropped, and that's what we typically associate with free falling, an object that is dropped from a given height and it falls down towards the center of the earth. That is, it falls towards the surface of the earth, and as it does so, again, if we ignore air friction, it will be accelerating at a rate of 9.8 meters per second squared. And we saw then that there are certain criteria that we use in order to define and to identify that type of free fall. Okay, and we will practice that as we work through the problems today. Okay, the second type of free fall then is very similar to the first type of free fall, and the only difference then is that we are actually, instead of dropping an object, we are tossing it down. We are tossing it in the downward direction. As a result, then that particular object has an initial velocity that is not zero. It still accelerates. It accelerates at a rate of 9.8 meters per second squared towards the center of the earth, okay, down towards the ground, but it now has an initial velocity that was given to it because we actually throw it down to start out with. Okay? And so that's the second type of free fall that we talked about yesterday. The third type of the free fall is the most complex of the three, and it involves a motion that we don't typically associate with a free fall, and that is an object that is thrown up. Okay? An object that is tossed upward is in free fall. Now, it's in free fall even though we don't associate the upward motion with free fall. But remember, the way we define free fall is any object that is going to be moving towards the center of the earth, or more importantly, it has a gravitational acceleration of 9.8 meters per second squared down towards the center of the earth. And so an object that is tossed up has that acceleration as it moves up, and also has that acceleration as it moves down. And so we were able to diagram that motion yesterday. So I'm going to start here with you, with you on this one here. And so remember, for an object that is thrown upward, we want to break it up into its two separate motions. You have the upward trajectory, and then you have the downward trajectory. Okay, and I've identified here the characteristics of the upward trajectory and the characteristics of the downward trajectory as well. So you want to split it up. Okay, you want to split it up so that you can deal with it in separate motions. Okay, so during the upward trajectory, we talked about this. It has an initial velocity that is not zero because we are throwing this object up. And so therefore, remember, we said that whenever we toss an object either down or up, we are dealing with the velocity after it leaves your hand, after it leaves the source of its motion. Okay, and so therefore, it will have an initial velocity that is not zero as it moves in the upward direction. Okay, all right. So with that said, let me go ahead. Okay. All right, so with that said then, it has a displacement that is positive because it's moving up. And remember then, we said then that we will just follow convention, and we'll say then that along the vertical, okay, up is the positive, down is negative, and so it will have a displacement that's positive, but it's acceleration though. It's acceleration. That is the only force acting on it is gravity. Gravity is down, and if the only force acting on it is downward, the acceleration will also be downward. And that downward acceleration will be at a rate of 9.8 meters per second squared. So the acceleration is negative, the velocity is positive, and therefore it will be slowing down, which makes sense because as it slows down, it's going to reach a point where it stops. Okay? And it stops at the very top of its pathway, at the apex of its path, it will stop and it will have a velocity of 0. And it makes sense because any object that's tossed up has to basically turn around and come back down. And before it can start coming back down, it has to stop its upward motion and then turn around and come back down. Okay, so what happens here is during the upward trajectory, the object will be slowing down. Stop, and then it starts its downward trajectory. And in its downward trajectory, it will have a velocity after it leaves this point here that is going to be negative, and it will not be 0. Its displacement will also be negative, but its acceleration will still be the same. So if you notice here, the acceleration in the upward trajectory and the acceleration in the downward trajectory are exactly the same, negative 9.8 meters per second squared. Now, why does the object speed up on the downward trajectory? Because the velocity is negative and the acceleration is negative, and so they're both pointing in the same direction. Object will start speeding up, and it will continue to speed up until it hits the surface of the Earth. Okay. All right. So that's the third case of the free fall. Yes, it's a little bit more complex, but again, like I said, if you break it up into its separate parts, it becomes very, very manageable. Okay. All right. So let's go ahead then. You can also with the third case of the free fall, you can make things a little bit simpler on yourself if first and foremost you're able to identify then whether the motion is symmetrical or non-symmetrical. And let me explain to you what I mean here by symmetrical versus non-symmetrical. Okay? All right, so you can imagine the pathward here. Okay, so the path of the object here is drawn here. So it's tossed up and then it comes back down. The symmetrical motion itself, and I'm going to divide this line, I'm going to divide this motion in half from the top here. If you divide the motion in half here, okay, so let's go and do that. Let's draw our dividing line right there. Okay? If you draw this dividing line, then the motion is symmetrical. It means it moves up a certain distance and it covers the same distance coming back down. So there's a line of symmetry that can be drawn across this motion here. This parabola here, you can draw the line here and it splits it up exactly in half so that the left-hand side is identical to the right-hand side. That's what we mean then by symmetrical motion. Okay, the symmetry here is based on this line of symmetry that we've drawn right here. If that is the case, if we can identify symmetrical motion here, and then these characteristics will come into play. First and foremost, the time, so T up versus T down. So we're still going to split up this motion from the upward, okay, upward trajectory here. So this is going to be representing the upward trajectory. This is going to represent the downward trajectory. So we're going to split it up into two separate motions. So this is going to be the downward, okay, all right. And so with that said then, T here represents the time, okay, which means then the time it takes to go up. So time up versus time down. And this will only be true for symmetrical motion. Those two times will be exactly the same. The time it takes the object to move up to this apex. So remember, at this point here, the velocity at the height is going to be 0 meters per second. The time it takes to move up to the top, okay, and the time it takes to from the top to move back down to where it started, okay, is exactly the same. So this is time up towards the apex, and this is time down towards where it started. Okay, all right, so that would be the same. Now, with that said, then, okay, if we consider this, then, okay, the velocity here, okay, the velocity at the initial and the velocity in the final, okay, and so when we say this, this is landing or getting back to the point where it started. Okay? So the velocity at the start and the velocity at the final, the magnitude will be exactly equal to one another. Okay? They will be exactly equal to one another. However, the only difference then is the V final here will be in the negative direction, whereas V initial will be in the positive direction. So these two velocities here will be exactly equal to one another. They are not 0 now. Remember, we're not talking about the velocity as it rests in their hand, but it's the velocity as it leaves and the velocity as soon as it falls right back to where it started, okay? And so with that said then, the velocities will be, the magnitudes will be exactly the same, okay? However, the signs will be different, okay? And so actually, if you consider this relationship here is true at any point along the pathway here. So let's go ahead and take a look at this pointer. So the V1 here up versus V1 down, okay, will be exactly the same. The velocities at this point here will be exactly the same as it moves up. And when it gets past, gets to this point here, the velocities will be exactly the same. The only difference then again will be the sign. Okay, so this is actually true for any point in this symmetrical motion. Okay, so the positive up, negative down, but the velocity with exactly the same. So you want to make sure you keep in mind then that with symmetrical motion, with an object that is moving symmetrically with in the second free fall here, then these characteristics will always be helpful for you. Okay? All right. So you can imagine then, in going back to the time here, okay, so the total time, okay, total time will be equal to time up plus time down. But if they are exactly the same, you can imagine then that you can take the time up or time down, double it, and you will get the total time right there. So that's something a little bit extra that'll help you work out these problems. Good. All right, what if the motion is not symmetrical? What if the motion is not symmetrical? Okay, so for example, and let's take a look at an example here. This motion is not symmetrical because let's go ahead and let's draw our line again. Let's draw our line, and you'll see then that if we split this in half, the motion is not symmetrical. Because if you take a look at this here, okay, the line here is longer than the upward motion here. Okay, the upward motion is further than the downward motion. So there is no symmetry in this motion here. If that is the case, then what you have to do then is just make sure you break up the motion into its upward and its downward trajectory, and you treat it as two separate problems. You treat it as two separate kinematic problems, and that's the only thing you can do. Now, what is true then, though, is what you can do is you can compare times, you can compare them, but the idea then is if you don't have symmetry here, if there is no line of symmetry that you can draw in its path for the pathway here, then you make sure then that you just break up the motion into its separate parts. Okay, so you got to break it up into the upward and you got to break it up into the downward. But make sure you keep in mind, though, as you do so, the acceleration up and the acceleration down, what's true about these two, that they are exactly the same. Okay, so the acceleration going up is equal to the acceleration going down, and both of them are equal to negative 9.8 meters per second squared. So that's the only thing that we can say that's true about the upward and downward motion. Apart from that, you treat the two problems, you treat the motion as if you're working out two separate problems. Okay? All right, let's go ahead then. Let's work through a couple problems here. I want to work through some problems here to help you. Okay, let's take a look at this first problem here, and let's work this one out together. Okay, so make sure you read this first. And first of all, you should identify the free fall. Okay, so read this problem then and identify what you were given. I would suggest you follow the exact same methods that we used to solve for problems involving objects moving along the horizontal. Okay, so the technique is the same. We're just going to apply it to an object that is moving in the vertical direction. Okay, so make sure, let's take a look at what we have here. We have a ride here, and so we were told then that this ride here is a vertical ride. It starts from the top, and then it drops the person down, drops these people down. As soon as you recognize that, as soon as you read that, you should be able to identify already that this is a free-falling object without it telling you that, but it tells you here that it is a free fall. Okay? All right, so they tell you that the time interval for which it falls, okay, so this is a free fall. Now you just have to identify which free fall it is. Is it the first one, or where the object's being dropped, second one where the object's being thrown down, or the third one where the object's being tossed up and then comes back down? Hopefully you recognize which one it is here, okay? And so with that said, then we want to find the velocity at the end of this 1.5 second time interval, and also we want to find then the displacement, okay? All right, so which type of free fall is this right here, okay? And so this clue right here, helps you. It tells you that it starts from rest, which means then that the initial velocity is going to be 0 meters per second. This free fall then, folks, is the first type of free fall. Okay, so free fall number 1, and we'll go through those characteristics, but hopefully you're able to identify that from the clues that are given to you in this problem here. So once you have those clues established, let's go ahead then and let's solve for this problem. Okay, let's go ahead and solve for this problem and let's see how it works out. Okay. All right, so what I'm going to do then is, what I typically do then is I just go ahead and I redraw the problem again. So I draw our free body diagram. So free body diagram involves our object there. There's the ride at the top. Okay, it starts to fall downward. Okay, so let me go ahead. That's bad. Okay, let me just throw an arrow in here. Whoops, sorry. Okay. And so we know then that it's going to be falling downward. So let's plot our free fall there. Okay, so this is an object moving in the downward direction. It is in free fall. Okay, let's go ahead and label this object there with what we know. Okay, we know then that the object, and this is again free fall number 1. This is the free fall case number 1, in which then right here, let's go ahead and identify this here. How do we know that? Because the initial velocity is 0. It starts from rest. So the initial velocity is 0 meters per second. Based on what we have here then, if this is an object in free fall, we know the acceleration. The acceleration then is going to be g, which is a constant, which is given to us, which we know then is negative 9.8 meters per second squared. That we know as well. We know that because this is a free fall. And they don't give us this, folks. Make sure you understand. This is not given to you. This is something that you're expected to know because this is an object in free fall. So make sure then that this part here, this acceleration, you memorize, folks, because that you need to know. And this is easy because any free fall has this acceleration. Okay. All right. So what else do we know? We are told then that the object moves, okay, for a time interval. Okay. So the time interval here, okay, the time is from start to finish. So this will be the final here, the final point, okay, of 1.5 seconds. Okay, so we have 1.5 seconds that it continues to fall. So what they want us to do then is they want us to find then the final velocity. They want us to find that, and they want us to find then how far it falls. They want us to find then the displacement as well. So they want us to find both of those as we go through this. Okay. All right, so how do we solve for this one? Let's go ahead then. We're going to use the kinematic equations. So let's go ahead and write down the kinematic equations that we will need to solve for this. And there are only 3. Okay, so we have 3. The first one then was V final is equal to V initial plus A times T. That's the first one we have, and this is what we learned previously. We also had then delta X. In this case then, I'm going to substitute delta X for delta Y because we're moving in the vertical direction, okay? And that's going to be equal to V initial, or V times T, plus 1/2 A T squared. And then finally for the last one, then we have then V final squared is equal to V initial squared plus 2A, and again, delta Y because we're moving in the Y direction. Okay. All I did here was take the kinematic equations that we learned in the previous section, and I just substituted in Y's for X's. Okay. All right, so we want to find V final here, folks. Okay, and let's see what we have. Okay, so can we use this first equation to solve for V final? Well, do we have V initial? Yes, we do. We have V initial right there. Do we have the acceleration? Yes, we do. The acceleration is right there. And then do we have time? Yes, we do. So we have time there. So for the very first calculation, let's go ahead and work this one out together. Okay. To solve for V final then, okay, we can just use this first equation there, which is going to be, so let's go ahead and solve for V final. It's going to be V initial plus A times time. So we can go ahead and do that. And again, we're going to be solving for these problems exactly the same way that we solve for the problems or objects moving the horizontal. Just now we're going to apply the vertical motion. Okay? All right, so with that said then, the initial then was 0 meters per second plus acceleration is negative 9.8 meters per second squared, and the time interval here was 1.5 seconds. Okay, so you plug that in to your calculator, then you end up with a value that is negative 14.7 meters per second. Okay, and hopefully this makes sense because the object is falling down, so it's still moving in the negative direction, and so this is the velocity right before it hits the ground. Okay, so obviously when it hits the ground, it's no longer in free fall, so we don't count that. Okay, so this is the velocity right before it hits the ground. Okay, so there it is. Okay, let's go ahead then and let's solve for delta y. Okay, so that is the total displacement that we have here. Obviously, we're not going to use equation number 1. It doesn't have displacement in it at all. Okay, and we use equation number 2 to solve for this one. Well, there's displacement. Okay, we have velocity here, but the question is, which velocity are we considering here? Which velocity is that? Okay, and so we have that. Okay, so this is going to be the constant velocity. Okay, so let's consider that. We have that if we consider what we have here, and then we have time, acceleration. Yes, we have that as well. Can we use this third equation to solve for this? Okay, well, let's consider this. Do we have v final? Yes, we do. We just solved for it. Do we have v initial? Yes, we do. We have it right here. Do we have acceleration? Yes, we do. We have that as well. So we can solve for delta y as well. That means that we can use either one of these to solve for it. Okay, so I'm going to go ahead and use this first one here, so just so we can deal with this part here. And I'm running low on time. Okay, so let's go ahead and use that first one. 1/2 a t squared. Okay, all right. So with that said, then this is constant velocity. Okay, the velocity during this time interval here is not constant. Okay, and so therefore the only part that's constant is this 0, this 0 right here. So therefore we're going to use the initial velocity right here and plug it in. Okay, so let's go ahead and plug that in. Okay, so we have 0 meters per second. That represents kind of the initial velocity. Plug it in. The time interval here for the total moment was total movement is 1.5 seconds. Okay, and then we have the acceleration then is negative 9.8 meters per second squared. And then the time interval here is going to be 1.5 seconds that it accelerates. And we're going to square that. Okay, so you plug that in, then you'll get your displacement then as being negative 11 meters. Okay, and that's what we have there. What I would like you to do to finish out here, folks, is I told you that we can use this equation right here as well. So I would like you to, you should be able to get the same answer, folks. You should be able to get the same answer. I want you to use this equation here, initial squared, plus 2a delta y to solve for displacement. Okay, so you have the answer right there. Okay, so plug it in and see what you get. Okay, and you confirm that. So I'd like you to do that for the turn it in. Okay, so I want you to go ahead and use that equation, write it out on your paper, do the work, and then make sure you submit it, and show yourself then that it should work. Okay, so go ahead and plug it in and get that done, submit it, and then we'll meet on Monday. Okay, and then we'll just meet for a little bit on Monday, and then I'll let you go, and you can finish. Go ahead and watch your lesson, do the lesson for Monday. But let's meet live on Monday. I will see you folks then. If you have any questions, come on by and see me. I'll be available after school today from 1:30 to 2, okay, and then and get your questions answered. Okay. All right, folks. Have a good day. Have a good weekend. If I don't see you this afternoon, and I will see you on Monday.